Good morning, everybody. We're drinking green tea. And I was rewatching yesterday's stream and I realized I had some bad habits. I say, you know, and right way too much. So it's time to stop doing that. Right? You know? I also realized that chat was full of idiots and I shouldn't listen to them. So there's that. Okay, so let's get into what we're doing today. Oh yeah, we're gonna keep it on subscriber only chat. Subscribers are slightly less stupid than the average chatter. Yeah, I realized that I have to assume that there's a world of people out there who watch these streams and they're different from the type of people who comment in chat. Because if those people don't exist, then I don't know what the point is. Okay, so we can break this down. This is this command run in tinygrad, and we can break down all these things. There's a bunch of, okay. I need to work on explaining things better. I have this internal language in my head, maybe it's my chain of thought, which often makes it difficult for me to express what I'm thinking. And it comes out in some kind of confused pigeon where I shouldn't be doing that. I should be communicating more clearly. So we can break down why. See now, right now I'm thinking this, but I'm also thinking I just want to paste this into ChatGPT, which I logged into. What is this? Question, enter. I just like to see what ChatGPT thinks of. Can you break down the reasons tinygrad is slower? This is on an Apple M3. Let's see how much ChatGPT knows. No, these aren't right. Okay, ChatGPT was useless. Okay is another one of my verbal tics. I need to stop with the verbal tics. If you don't have anything meaningful to say, don't say it. We can break this down into several different reasons why certain operations are slower. And for each one of these, there's almost a different reason. But it's not like it's not a crazy long tail. There's a small number of things which we can fix and achieve performance that's better than PyTorch. So before we focus on just the negatives, we can focus on the positives. These are faster in tinygrad than in Torch. These are faster in tinygrad than in Torch, but certain other things are slower. It's not as bad as you might think, and we can get into the reasons why. So is another verbal tick. A 1-by-1 add is a very fast kernel. You can see how fast it is here in Torch. Put myself up in this corner because we're going to be using this today. A 1x1 kernel is very fast, so we're limited entirely by kernel dispatch speed. While tinygrad's very good at chaining multiple kernels together and using all the graph APIs to do that, when you're just doing a single kernel, you're limited entirely by how many layers you have to go into to dispatch. I actually improved this a bit. This is external benchmark kernel launch. That's for Metal, but if we do it with LLVM, it's taking about 0.01 milliseconds or 11 microseconds to launch a kernel, and it is going through a bit of Python in order to do that. So this Python can be made a little bit faster, and that's what will close the gap for this first one. But that one's not all that interesting. These cats are twice as slow because I'm pretty sure the code is bad. I'm pretty sure the UOPs are bad. So if you want to take a look at that, you can go in here. Take a look at it with Clang. The same slowness in Clang. For your debug equals 4, we can actually look at the code. So this is the code for cat, actually. So let's see what it is. So this is cat, and what cat is doing, let's read it. It's just concatenating the two tensors along an axis. But tinygrad doesn't have a real way to express memory operations like this. So the way that it's doing it is it's making a big empty tensor, and then it's adding, it's taking the first tensor, putting zeros over here, right? First tensor, don't say right. First tensor, zeros over here. Second tensor, zeros over here. And then it's adding those two tensors together, which functions as a cat. If the rewrite was smart, it could figure out that it doesn't need to do all those extra loads, but I'm not sure how smart the rewrite is. So here we can see the generated code up here. And no, the rewrite's not smart. So take a look at what's happening. This is the full 512 that it's catting. This is a Boolean, which determines whether you're in the second half or the first half. Then this is, if you're in the first half, it reads from the first one. If you're in the second half, it reads from the second one, and then it adds those up. Unfortunately, yeah, this is a very slow way to do this. What should really happen is that this loop should be broken into two loops. This variable should break this loop, and then you can do just the first one in one and just the second one in another, and you can avoid all of this extra stuff. You don't actually have to do the add. So maybe there's just a simpler way to do this. Instead of breaking the loop, do you want to say hi?
Yeah. Do you want this?
Sure. What did I get?
Vitamins.
This is
Hi.
Amanda.
Hi. Nice to meet you.
She brings me pills. What are these ones?
It's a B complex.
What happened to the purple B complex?
So we looked at exactly what was in the Monster Energy drink
Oh.
that you liked, and we tried to replicate it in vitamin form.
Where did this one come from?
The drawer.
It was in the drawer?
It was in the drawer.
Wow.
I'm not trying to poison him, I promise.
What's this one?
That's zinc quercetin echinacea.
What's echinacea?
It's a plant to help you with the congestion.
Do I like plants?
Do you like animals? Do you like minerals?
What's this one?
Yeah,
you can see
oh
yourself.
my
You can
goodness.
see yourself on the
Hey.
camera. We're talking about.
That's magnesium L-threonate, neuromag.
Oh, that one sounds
Or
good.
nootropic.
Let's eat that one.
The other ones are good too.
What's this one?
So that's the NAD plus precursor.
We're on the Brian Johnson pills team. We eat pills. You should see. She eats a lot of pills.
He barely eats any pills.
This is not that many pills, but pills are part of a balanced diet. I've ever seen I got my Frosted Flakes, my orange juice, my banana, and my pills.
Yep. All right, I'll leave you to it.
Bye.
Enjoy your pills.
We have pills. We have to eat them. So it's probably simpler to fix this by, this doesn't have to be an add because you're adding 0 there. So we can look at what's going on maybe here. Where's the best place to look at this? Yeah, so like you kind of have to just look at this pattern and know that these are gated. You can see these indexes are gated by this comp.lt and comp.any, and then you don't actually have to do this add. Instead of doing a gated, you kind of still want the load to be gated. This isn't that easy, but you can look at this code and see why it's considerably slower than Torches, which is just going to basically do 2 mem copies. This should be 2 mem copies, but due to the way that that's written in tinygrad, it's constructed like this. We used to have a really slow A range, but we fixed the A range to be fast by using rewrite rules. I can show you where they are. So when I talk about rewrite rules, there are these sort of things. I don't know if the A range one is actually here. More rules in rewriter. Maybe the A range one is here. Yeah, there's too many rules all over the place if I can't just simply keep this. In my head. So some of these rewrite rules you can see are really simple. They're just things like x plus 0 equals x times 1 equals x. Don't say so. Where's the A range stuff? Here we go, it's in rewriter. Wow, it's gotten so short now. It's just called A range loop folding. A ranges are written through this construction where it creates a diagonal tensor of ones and then sums them, and that gives you a range. The reasons to do this, you think, so a range is really simple. I can just take the the loop variable and plug the loop variable and stick the loop variable in. But there's a lot of edge cases, and that's really hard to express in such a way that it fits into the tinygrad framework. Similar with this concatenate thing. It's really easy to express the addition of tensor 1, zeros, zeros, tensor 2, tensor 1, tensor 2 concatenated. So there needs to be rules written like this to simplify this concatenation. And that's why this one's slow. So we've explained this one, and we've explained this one. I'm not even sure what that one is, but it might be the same thing. Let's see what array packing is. Shape, permute, contiguous. That can be a whole lot of different things. It's interesting also how high RAM bandwidth this is getting. It's much higher than all the other ones. In theory, this chip has 400 gigabytes per second of RAM bandwidth, but I'm not sure what the maximum achievable throughput on a single core is. So all of these tests are single core tests. Now we get to convolutions. So this convolution is faster in tinygrad, about twice as fast. These two are a little bit slower. This one, I'm not sure why. This one, it could potentially be Winograd. So we can try that. Try it over here and come back to it later. That explains the convolutions. I have no idea why exp is slower. This might have to do with, we have our own implementation of exp. It's possible the CPU has a built-in one. We have our own, we call it the transcendental library. We don't actually emit code for exp on CPU because often on CPU you're calling into these libraries which are doing a lot of instructions. And if you've ever read Elon's rules for what are Elon's rules for process? Half of why ChatGPT is good is because it doesn't have ads yet. The beauty of these LLMs is it's going to be hard to build a moat like Google, where Google spent a lot of effort focused on optimizing the long tail of search, and that's a reason that they became really hard to compete with. They also had a data advantage where people would want to get their stuff into Google, so everyone would help Google index them. This may become true for LLM companies also, but due to the nature of LLMs being basically you just can shove anything into them, that persistent indexing advantage that Google had that made the web crappy for 20 years is probably gone. So this is, yeah, wow, see, this is much more beautiful than every time I've tried to Google this. Thank you, ChatGPT. Make the requirements less dumb. Try to delete part of the process, simplify or optimize. I have one, like, I call it rule 0. I really like these rules, but we have rule 0, and rule 0 is surface all complexity. If you have something that is we have a supplier and we can get this, or we have a library and we can import this, you don't really know what that's doing. I want to bring that complexity as close as possible to the surface, and that's kind of the philosophy in tinygrad. We have I can show you the exp rewriter in transcendental. So this is our function for exp. And for some reason, it's twice as slow as the one Torch is using. So somebody can look into that. But I think that is unrelated to this. And it's certainly unrelated to this. And it's also unrelated to this. So those are three separate problems, but they're all approachable. Gem is an interesting one. Notice how much worse we're doing on Gem. Also notice how Gem in Torch is a big outlier for the flops. The reason that it's a big outlier is that it's using different hardware. So the Apple M series chips have something called the AMX. And it is a, again, this is where I struggle to communicate. I have internal ways that I think about this stuff that I don't always verbalize. This is a multiply accumulate array. I put this in the document yesterday. Those docs are now live on docs.tinygrad.org. We go to speed. So multiply accumulate array is a MAC array. The main value of these is since they are 2D, they create an n-squared ratio between the compute and the input data. I understand when I write a sentence like that not too many people are going to just read that sentence and understand it. I don't know. I don't know. I gave a talk in Poland last year about tinygrad stuff, and it was clear that nobody understood anything that I was saying. When I write something like that, it's interesting because I've had someone start to do this to me, whereas they'll write things like this and I don't understand them. And this is not a virtue. It's not a virtue to not be understood. You should be able to make things understood simply. This picture explains this better than the sentence does. The X and the Y are the O of n inputs, and this accumulation is n squared. You can see it's n squared because it's a square. It's a multiply accumulate array because it's multiplying X times Y and then adding it to Z. This isn't what GPUs use. GPUs use tensor cores because it's hard to fit this 2D output register into a GPU paradigm nicely. It's much easier to fit the tensor core paradigm, which has the same size as the inputs. But they're similar. The reason that Torch is so much faster here is because it's using the AMX. How'd we do when we enabled Winograd? Oh, this one got faster. This one got slower. I didn't realize these were all k equals 3. I thought one of them was a 5 by 5 convolution, but I guess not. So this one's faster, this one's the same, and this one's slower when we switch to Winograd. Torch probably has good heuristics for this. Winograd's an interesting one where it's not written as rewrite rules, but maybe we could write it as rewrite rules. That would be the right way to do this, to write it as optional rewrite rules in tinygrad instead of, right now Winograd is just implemented in tensor.py. If we go to tensor.py and we look for Wino, you can see that this is the normal conv logic, and then this is the Winograd conv logic. So sometimes Winograd's faster, sometimes it's slower. I'm not that worried about that. Those are only off by a little bit. These are using the AMX, and that's why there's a huge disparity. Now, tinygrad actually supports the AMX. Unfortunately, it's not supported in that. Let's let this run for a little bit. It's supported only in Clang. We have a bounty lock on the guy who originally wrote the AMX code for Clang, adding support for the AMX to LLVM. But unfortunately, the AMX is still slow. And the reason the AMX is slow is the same reason that GPUs use tensor cores and not MAC arrays. This register is special. Let's see if we can trigger the AMX on something small. Yeah, this is triggering the AMX. So this is the AMX here. Unfortunately, you can see what this code is doing. Even though it's using the AMX to do the accumulate, it has to load it in and out of this register every time. And the data path into and out of the AMX is just main memory. In order to fit it into the tensor core paradigm, these things are doing loads and stores to main memory every time it does this. Every time it does. This is math. These are memory accesses. I wish this was... Unfortunately, yeah, this is not documented great, and it should be documented better. So 4 is LDZ, 5 is STZ, and this is loading and storing to that Z register. What needs to happen is that tinygrad needs to understand that it doesn't need to load and save to the Z register every time. This stuff also can't be optimized by LLVM because it's inline assembly. So there's no way that something lower level is going to optimize. We have to see this at the tinygrad level. And then this accumulator being created in all of these, what are effectively registers, and they're probably being stacks filled because there's many of them, should just be that internal Z register. And tinygrad needs to understand that. I should add a bounty for this as well, if I don't already have one. I might have one. Yeah, I do. So that's this here. Good, it's priced at what I was thinking I was going to price it at. So it's $500 if you can fix this. It's not that hard to fix. You just need to express these loads and stores and then get the loads and stores to cancel out if there's just a store followed by a load, even if that's through a loop. So unfortunately, even though we have AMX support, it's actually slower than using... This is using ARM Neon. Neon is ARM's SIMD extension, similar to AVX on x86. So that's why these ones are slow, and that can be dealt with separately. Now, what's interesting here is if you get the AMX to work in tinygrad fast, it's likely that the AMX can also be used for convolutions. And then we can start getting numbers that look like this, but instead faster than Torch. So we could be 10 or 20x faster than Torch on Apple CPUs. The AMX is available in the M1, M2, and M3. I believe it's also in the M4, but they also have a different way of accessing it through ARM extensions. There's something I read about this. I don't have an M4. I think it's going to be very similar if you make the AMX fast to also make that fast. And then we can get gains not just in gems. Because of the way tinygrad's written, we generate the code every time. So this is calling into some library, and the gem library supports AMX, but the convolution library doesn't, especially when you get to one-by-one convolution. So a one-by-one convolution is a gem. There's no difference. I say nah, actually, that's not a one-by-one convolution. That's that's still 3x3, but a one-by-one convolution is a gem. All right, think about it. It's a batched gem across your width and your height become a batch dimension for your gem. This is what I want to focus on today. Why are these matvecs slower? That doesn't make all that much sense. Somehow Torch is getting much higher memory bandwidths than I am. Maybe the first ones to focus aren't even those though, because I think that these are the same problem as these. How is Torch capable of doing a sum faster? So it's doing a sum and getting 74 gigabytes per second, whereas I'm only getting 47 gigabytes per second. I think the first thing to do, and what we're going to work on, is benchmarking how fast we can get a single core to read through memory. I can't imagine, actually maybe I can. No, I can't imagine that we can't do, so sum is just summing all of these numbers together. I can't imagine that that sum is somehow that is flop bound and not memory bound. Load this big chunk of memory while accumulating the numbers as we go. Let's eat some more pills. Does chat have anything useful to say? Thank you for gifting subs. I'll also take a minute to talk about this feature. We have a $1,000 bounty to be matched also by TensTorrent. So you might get $2,000. Corsics also said he'd personally match it for Wormhole if you want to get tinygrad working on TensTorrent hardware. TensTorrent hardware has some unique characteristics. It doesn't fit perfectly into the GPU programming model because of how different its memory system looks. Take a minute and talk about this. So this is Grayscale TensTorrent's original chip. I believe that only certain cores on the chip are capable of accessing memory, and then you use the communications primitives between the cores to send things from the memory to the other cores. This is very different from a GPU. A GPU, no cores have privileged access to memory, and they spend tons of transistors and power making memory access fast. GPUs are load store machines. They are designed to make random memory access as fast as possible for a huge number of cores. And they have these incredibly large power-intensive caches in order to do that. If you've heard about the Infinity cache on AMD, NVIDIA also has a very large L2 cache. These things are power-intensive and big, but they provide fast memory access for all of the cores, whereas TensTorrent has a different sort of architecture. And then you can get to things like the Google TPU, which go even further. Well, the Google TPU is kind of similar to the TensTorrent chip. I do think they have a shared no, the new one, that's an old one. Here. Well, that's really, okay, that's even more, I think it's changed. I think it's a little more generic like that. a little more generic than that once you get to yeah, forget the TPU v1. That thing's confusing. I don't know what that's saying about DDR3, but the TPU v2 seems to be similar to what is used in all the modern stuff. They have a DRAM that's only connected to an SRAM. And this DRAM to SRAM path is explicitly managed. The edge TPU. What if this stuff's actually in tinygrad proper? Look at how unusable the internet is too. Look at all the ads and crap. Here. So these are TPU v2s. But there's a lot I still don't know about this. This was one evening of trying to look into how the TPU works. The basic trade-off here, there's much better diagrams of this. Let's see if we can find them for the modern ones. I have to get rid of DuckDuckGo. I don't know why I'm using DuckDuckGo. It's just the default in Firefox. Or no, this isn't, no, it's not the default in Firefox. It's the default in Chromium, on Google's Chromium. Why do they add these stupid things on top of it? There's this conference called Hot Chips, and it has all the best. On a Japanese VPN because ChatGPT is not available in Hong Kong. This is what the modern TPU looks like. So this is the memory here, and you can see that the memory is not even connected to the compute core. They just have this CMEM, which is effectively SRAM, between them. And you can look also at the Qualcomm DSP. We're working on a contract to make this fast. Chips and Cheese is a good one. Chips and Cheese is one of my favorite. They really break down. This is a beautiful diagram. They make these diagrams and they're awesome. This is how the Qualcomm DSP works. And you can see that the DSP looks quite similar to the TPU. It does have this path. So maybe the compute can directly access the memory. On the DSP, the compute can directly access the memory, but there's also this thing called the TCM. And the TCM is basically the same thing as the CMEM. There are these on-chip SRAMs that have much higher bandwidths than the DRAM. Yeah, they also added a tensor core to the new DSPs, but I'm not targeting that one. These are all the things you have to think about when you're thinking about how to actually get speed on a platform. You have to think about all of these paths and how to basically saturate all of them at the same time. You want to overlap as much as possible your memory accesses with your compute. You want to keep every piece of the processor fully saturated. You want to saturate the ALUs here. You want to saturate this interface here. You want to saturate this, whatever bandwidth you can get out of that here. So where does that leave us? Why is this slower than Torch? I think we will dig into that and we'll write a minimum C program to try to spin through memory as fast as possible using ARM Neon extensions. So instead of just creating a dumb C runner on our own, we can use pill. So let's focus on these two. Let's focus on these reduces and see why we're getting worse performance. Think of how to write this. I bought a TV last night. Pretty nice. The Max is way slower too. I think I did look into this once and found out why this was. It's the RAM, that stuff doesn't really matter. It's kind of annoying. Let's actually just do this. It's a little annoying because these are tinygrad kernels, and when I'm using Beam, no. You see why that's slow? That's first going to create them in. don't like having the other noise in tinygrad. Especially because random is, I mean, it works, it's annoying, right? So now it's just a copy in. Don't say it right. There we go. So now it's a copy in, takes 11 milliseconds. It's actually much faster to do the randomness in tinygrad than it is to do it in NumPy, but there's a lot less noise when I do it in NumPy. Sorry, I gotta make that one smaller. The kernel that I want to focus on is a.sum. Why is that giving us so much higher throughput? Oh, we're on metal. Okay, there we go. Now it's slow. You can see on metal it's very fast. We're getting 20x the throughput on metal, and this isn't on Apple chips have unified memory. This isn't flop bound on the CPU. So for some reason, the GPU is capable of accessing the memory 20 times faster. I'll also note here that there's 2 kernels. This is probably something that's mostly optimized for GPUs, because in GPUs, you want to make sure that you're using all of the global cores, and then it just does a second. It does a 2-stage reduce. First using all the global cores to accumulate individually, sticking that back to global memory, and then having one kernel, which sums over that little part of global memory. That's the kernel 3 right there. So we can try disabling that and see if things get faster. Let's also do that sum in NumPy and confirm that we're getting the same value. Seems pretty close. Cool. Let's just make sure we don't actually break the tinygrad code. I'm also curious how fast NumPy is doing it. That's not right. NumPy is doing it 3 times faster. How does that compare to Torch? This is 496. 496. Oh. Okay. When you beam it, we are faster than NumPy. We're actually crushing NumPy. Wow. That's cool, guys. We're crushing NumPy. It's just Torch is beating us. Or maybe... No, NumPy does not get faster. Regardless, I don't really care about NumPy speed. We can just get rid of that. NumPy is slower than tinygrad. Wow, what a shocker. The thing that I care about is this number here, this 44 gigabytes per second. Torch is getting 71. In theory, we should be able to get 400. Why is that number so far off? How do we do with Clang? Clang's basically getting the same thing. It's easier for me to think in Clang than it is to think in LLVM. Let's take a look at our code. I have no idea why that's not fast. Oh. No, maybe I do. It's accessing things here when it kind of shouldn't be. Those don't have to be accumulated like that. We can also, with debug equals 6, see the assembly that's being generated. What does this do, and why is it slow? Whenever I use ChatGPT, I always do check your understanding questions. It's wrong super often. Most people may not notice how often LLMs are wrong. It speaks with this very authoritative voice. I was asking it this morning about AVX 512 and Zen 4, and it was swearing that Zen 4 didn't support AVX 512, which is half true, half not true. I tweeted about it, but what it said was wrong. What the code does, loads data from memory into neon registers. Okay. It's performing this is why it's slow. It's having to do these shuffles, which it shouldn't have to do. Yeah, there's also, let's disable, we have that reduce splitting logic. Where is that reduce splitting logic now? Maybe it's in ops. It's still here. It's called split reduce op. So that's why it's generating the two kernels. I'll just show you quickly so we can do. You see that it's much slower on metal to not do that, to do that split reduce op. So look at the total difference here. It's a 6 millisecond difference. I'm also going to add in this. So there's two kernels. You can see that it's 0.27. Just resets it. Ignores that first one. We could do that with the RANs as well, but it still wastes some time. So that. Let's see if we can beam to make it faster. Why is it giving me that? Made it a little faster, but still nowhere near this original speed. Some like exiting issue. I don't know why that's happening. That's also annoying. Move that to debug equals 3. Push that later. Because they're all opening LLVM. All the children are opening LLVM. They kind of have to. Well, actually, they don't. If they're a child, they don't. But regardless. So much state in my head. So much different tinygrad state. This is my failings as a manager of the project. Your job as a manager is to unblock other people, is to figure out how to show other people a path to which they can contribute to the larger goal. There's also an aspect of motivating people. Maybe motivating is the wrong word. Being clear about the larger goal. Be clear about the larger goal and then show people how they can make progress toward it. I have to read more books. It's a Jim Keller quote. Most people who go into management will not read any books about the topic, or maybe they'll read one book. I read 10 books. I think the split reduce op difference is going to be notably smaller with LLVM. So it's still a little bit slower. We're still only getting 33 there. We're getting 47. So the split reduce op is still desirable. We're going to do this with Clang where I could actually read it. We have to avoid all that shuffling. I think there's a way to do that just in the don't beam. Maybe we want 4. The syntax is annoying. It used to be much prettier how this would print. Now it's so verbose now. I almost want to remove it. This is in debug equals 3. Verbose and garbage should be removed. Let's remove. What did it used to print? It used to print the lazy buffers, which were simpler to look at. Okay, this can be a problem for later. I want to look at the assembly. This isn't doing any more shuffling. But I see why that's slow, because it isn't doing any speed either. That generates the shuffle. Let's see if we can manually find things that are fast. Don't have to worry about optimizing that. We just want to get this number up. So we have a schedule. That's code's gonna fail now. Can't copy out on allocated buffer because you can actually run the schedule items. show you what this is. These are the schedule items. So we have to lower a schedule item. There should be an easier way to express all of this. There should be an easier way because it's a common operation where all you want to do is change the default optimizations. There we go. Now it works again. Complex logic here that needs to be removed. Where are those optimizations actually applied? If I start to forget how this works, it's hopeless for anyone. I mean, other people can figure it out, but this stuff should all just be way simpler. What do I have to do? Make it easy to alter the ops for a schedule item. Well, I will show you something we can do. So we have a compiled runner. We can create one of those. Go look at the exec item. So we got to do a runner prog equals. How do I generate a compiled runner? A program spec. I can get the program spec from the compiled runner with that. For now, just trivially shove that back in and confirm that still works. Still works? Okay, good. The difference is now we can replace the source code. Yay! These things are all data classes, which is really nice. And this is still this multi-stage reduce. I don't want it to be multi-stage. Let's focus on, let's make it a single thing. So how do I do that? This stuff's actually pretty easy. You can just do with context, split reduce op equals 0. Okay, now we're back to 1. The RTOL is a little bit off, but that's still very much correct. Okay, great. We're printing the source. Now we can put the source here. I don't know why that doesn't, why there's no, oh, I turned no opt on. Let's turn no opt off. Maybe. Yeah, that's like something. It doesn't matter. We're replacing the source here. So prog spec equals replace, prog spec source equals reduce source. All right. So now if I were to add like a typo in here, you can see that it crashes. It's pretty good. I mean, you have to know a little bit about the internal structures to do that surgery, but it's overall pretty easy. Okay. So let's just write something simple like this. We can switch to, oh, we can't actually switch to the, I change the name too. Let's call it reduce. Data 1 is 16 million inputs. If we want, we could even load this in. We could put this. I wish there was a way to like tell VS Code that this is. Oh, I broke it. Or I didn't. Oh, that was wrong. Whatever. Seems right now. Okay. So if I were to like nerf it and make it only go to like 15, you see that I broke the code and I get the wrong answer. Great. So let's look at the one that's optimized a bit. And let's, oh, I have to type def float 4 too. Let's look at the assembly that's being generated. Okay, so we're loading, I believe that's post increment style logic. No, that doesn't actually do anything. I don't know why that's there. Oh, we load twice because it apparently implicitly unrolled the loop. Here we're getting 11 gigabytes per second, and Torch is getting 71. So yeah, that's not a lot of gigabytes per second. An obvious change that I wanted to make is this. And then we can add them up later. Also just ask ChatGPT how to make this code faster. No, it's Python. How does that look? Oh. Semicolons. Spend too much time coding in Python, you forget to just put semicolons at the end of everything. Let's see, initializer for float 4. This. Okay, 27 gigabytes per second. That is an improvement. I'm sorry, 23 gigabytes per second. Okay, that's actually printing the wrong thing. That's not actually what's, no, it is, hang on. That's the wrong thing. Oh, it's recompiling it down here, I see. You can see it being recompiled down here and running here. So why is it, what is it, duping? You can see it's still the right answer. pretty sure it's in 128. Across all 4 lanes. Huh? What? Oh, wait, sorry, that's the loop right there. Okay, that's stupid. That's like barely even run. That's the loop. For some reason, the loop isn't fast. Okay, I mean, my next thought would just be to unroll the loop. Because like all the time in this thing has to be spent in that tight assembly loop, right? Yeah, I might not be able to. All right, let's just try something like this. Oh. 65. All right. That's better. That's more torch-like. Yeah, like that's the code I want tinygrad to generate. I don't know why I can't just generate it. Also, is this doing a fadd stupidly? There's one there. I like that it's combining the things. Oh, I should also be able to decide. Is that gonna help? No, same code. Okay. Let's try this. Okay, that's pretty good at 68. I'm pretty happy with that. But we need to go faster. Again, the theoretical limit of this is 400. I don't know why we're not getting 400. Because like our G-flops are not, it's not a lot of G-flops. That's minimal G-flops. So I think this has to do with sequential versus non-sequential. I was thinking of Sabrina Carpenter's A Nonsense Christmas, you know? Okay, well that's fast, but also wrong. Oh, yeah, because we can't do that. Wait, what? No. Huh? That's right, but slower. Okay, whatever. We don't want to do that. Let's also make another change here. These shifts are kind of stupid. Oh, where's the old one? Just do this and then do something like plus 16. Get rid of these shifts. I'm sure LLVM's optimizing this out anyway. But yeah, that should be correct. If I get my count of stupid parentheses right. Those are just nonsense parentheses. Just like A Nonsense Christmas by Sabrina Carpenter. Think about it, got me feeling Christmas. We're playing at the coffee shop this morning, you know. Okay, good. That's a good amount of nonsense. All right, 71 gigabytes per second. That's a lot of gigabytes. That's even more gigabytes than before. Well, that's only 66 gigabytes. Okay, that's not too many gigabytes. Ooh, 69, ooh, 72, 71. Oh, still the same RAM crap as yesterday. Okay, let's try something else. What if I create 2 accumulators? And do something like this. This doesn't really matter where these things get added, right? The stuff at the end is all like just irrelevant because it's outside the loop. 74. Okay, we matched Torch yet? Oh, we're beating Torch. Yeah. Sometimes. We want to avoid lane conflict. But how does this? I see. Yeah, there's like a dependency chain here, which we don't want. We should never want that. So you know what? We can even go crazier with this. Now we're doing reduction. $74. That's pretty good. $72. 65. 64. 73. Okay, it's already coalescing those into one read. Like this is effectively the same thing as one float 16, right? Hold on, let's just try more. You probably want to like use all the registers, you know what I'm saying? I'm not gonna start saying know what I'm saying. Know what I'm saying? Know what I'm saying? Know what I'm saying? There's too many know what I'm sayings. Oh. Oh, be fast, be fast, be fast. 75. Okay, but this still isn't getting at like that code looks very fast to me now. Just like look at this. Let's ask ChatGPT how to make it faster. Think about it, got me feeling Christmas. How do I make this faster? Let's eat this pill. Let's put some of these things in. Maybe that'll make it faster. I know fast math breaks some stuff. Oh, same code. Oh no, that's the same code because I disable compiler cache. Comma. Okay, well that didn't make anything any faster, so. Use simple loops that the compiler can easily recognize. Think about it, got me feeling Christmas. Use simple loops the compiler can easily recognize. I'm sure that plus 0 is fine. Oh yeah, simple loops. The compiler can easily recognize my ass. Why is this not fast? I put in fast math and fun roll loops. I'm not stupid ChatGPT. ChatGPT sucks. I thought you were going to be the top competitive programmer in the world. Why does this thing not optimize my reduce good? No, it's ARM. Oh, maybe it doesn't know that it's ARM. A common optimization is to maintain multiple accumulators in parallel, then do a final horizontal sum. But letting the compiler do it automatically. What? No. I tried letting the compiler do it automatically, and it got me that dog shit time. Okay. We need to go faster. Why can this be slow? I don't understand. Is it just slow reading the RAM? This is why I wish... Do I have a way to just shove assembly code in there? I do. We're gonna go to the assembly, boys. We're going to the assembly. Got me feeling Christmas. So one of the awesome things about tinygrad now is that the code is no longer, the code that's running here is no longer an SO. It's just assembly. We have one more pill. Let's eat this pill. We finished pills. Is Capstone only a disassembler? Oh, that's ChatGPT. That's not what I want. I'm getting rid of DuckDuckGo search. That's it. We're done with DuckDuckGo search. Ugh, it's going to DuckDuckGo search for Chrome settings. Search engine. Name. Google. Shortcut. Google.com. Add Google to Chromium. Think about it, got me feeling Christmas. There we go. What? No, how come I can't edit that? Why can't I edit that? Why can't I change this? change those things, but I can't change that. Okay, let's use Bing. Does anyone in chat know why I can't change that? Oh, should I try 03? You want 03? Okay, fine. We'll try 03. It did say 03. Doubt it's going to help, but we can always give it a try. Okay, this is a simple loop the compiler can recognize. Same garbage. 03 did not. I actually remember 03 being worse on some of the things I tested. We're going to the assembly, boys. It's the only place to go. Let's use Bing. I hear it's a good search engine. Capstone, assembler, Python. I think it can assemble as well. My eyes hurt. My eyes hurt. Am I the only one who feels this way? Explore more. 60 inspiring capstone project ideas. How many capstone project examples are there? Below, there are 150. Like, it's just retard. Like, the internet's for retards. Okay, this is only a disassembler. Unicorn, ARM code. Oh. Oh, Keystone. That's the one I'm thinking of. Yeah, we got that. Keystone. Yeah, y'all. Got a Keystone, you know. Got some Keystone, some Milwaukee's Best, some PBR. Going to the assembly. Think good, bad, it got me feeling. All right, no, I gotta stop. Oh, how do I delete like just that? Let's use ChatGPT and it's gonna delete one line. Delete up to the colon on each line. George, don't you know that you can just do this Vim bullshit? All right, human versus AI. Let's go. All right. Now, how many lines did it accidentally delete? Oh, by the way, AI won. Below. Oh, where was that? It's here. What? No. No keystone. Oh. On Mac, what do I brew install? Oh, OpenSSL. Do I have that? How do I not have OpenSSL? I already have OpenSSL. No. Dependencies should be illegal. Like I would use inline assembly. Maybe I should just use inline assembly. just YOLO that. Come on, ChatGPT, don't let me down. Think about it, got me feeling Christmas. No. I just like, don't say it. But I'm thinking it. All right, we built it. Good, that worked. Thanks, ChatGPT. I love, like, I used to waste so much time on crap like that. It's just kind of fast now, which is nice. All right, extra, reduce speed, great. Cannot import name KS from Keystone. Well, why is this a liar? Oh, Keystone Engine. I didn't even get the right Keystone. Pip3 uninstall Keystone, and now my shit's probably poisoned. What is Keystone? Oh, we weren't even trying to. This is not even the right Lundberg. Oh, it's an OpenStack identity. Oh, great. Okay, well, we had that on my computer for a little bit. Now we have Keystone. Pointer must have explicit. What? Huh? Because I imported Keystone? Oh. Clang. Clang. You gotta use Clang. Huh. Are we assembling this? Let's assemble something. Where did that example go? Right, create the assembler. Now we assemble into capital ARM bytecode. Programming. Invalid mnemonic. Okay. Ret. Well, if ret doesn't work, then maybe because this is included here. I don't know how Python works with that. So what you don't like ret? Just because there's too many enters? Ret. Come on, ret is a real ARM thing, right? Oh, what if I move R11? Does that work? Okay, well you can move R11, but you can't ret. Doesn't make sense. Can I move R11 here? Like that? Yeah, I can. How about can I move to when I do? Oh, of course that doesn't work. Oh, because it's ARM 64. Wait, ret's not a thing in ARM? Invalid mode, eh? Is there a mode for ARM 64? mode 64 maybe? Okay, invalid mode. Let's read the keystone code. Oh God. Okay. Oh, use KS mode little endian for ARM64. Thanks, ChatGPT. Great. Let's see if I can compile with all the crap now. Great. Thanks, ChatGPT. I love ChatGPT. ChatGPT is my new best friend. All right, we got a lot of ARM bytecode. So now when we look inside the EI object, we'll find a compiled runner, sure, but we want to dive into that compiled runner. And change the lib. What is that? That color. I don't like that. I don't trust it. Change the source code. Change the assembly. All right, so prog.lib equals. It's pronounced lib. Why do you keep saying lib? It's gonna be a from tinygrad. It's a device CPU program. We should just be able to shove the ARM bytecode in there. Let's see if it works. Compiled runner object has no attribute name. Oh, this part's back. I really don't know why it's that color. I set prog somewhere else? I don't know. Bytes like object is required, not list. Okay, well, I don't know why that's a list. I guess I didn't check it. Oh, bytes on bytecode. It's bytes, it's not a list. Okay, great. Let's see if it's working by messing with one of the numbers and seeing if it breaks. I don't know, let's put like a 1 here. Yeah. Invalid operand. Oh, who can write assembly code? Nobody. 30, that's gotta break some stuff. Didn't break anything. I'm skeptical. I'm very skeptical. I don't know. All right, let's see what's going on here. Should work. In case it's getting freed. I don't understand. Compiled runner definitely calls a lib, right? Oh no, it calls .prog. It doesn't call the lib. What am I doing? All right, now let's try to change that to 30 and see if it breaks. Definitely calls the prog. 0. Int object is not callable. Okay. Is that actually fine? Let's go back there. Okay, great. Seems to be working now. I'm not exactly sure why loading from 30. Oh, I know why it works. If we load from 20, it won't work. Take it back. It works. Works pretty much regardless of what I change. What? I don't understand this. If I don't loop. Okay, then it's broken. But how come I can change these and it's fine? That doesn't make any sense. That's very concerning. Okay, let's change this to rand n and hope it's centered around or what can I do? Random is between 0 and 1, so if I just subtract, no, it's going to be even slower. NumPy is slow, but whatever. Okay, fine. Wow, these things are really sensitive, actually. Okay, cool. Seems like it does something. I'm getting rid of that change to ops clang. It did nothing. It's on GitHub on the reduced speed branch if anyone wants to play with it. Okay, so what if I like read from like 80? All right, these things will do break things eventually. But like that one's broken too. Maybe I can do like a tall equals 1. Seems reliable. Floating point addition is terrible. Floating point addition is not commutative, it's not associative, I'm sure it's not transitive, it's none of those things. I'm not sure normal, I don't know. My point is it sucks. Like b plus a doesn't equal a plus b. A plus b parentheses plus c is not equal to a plus parentheses b plus c. Associative, commutative. I forget what transitive means. But I'm sure it's not that either. Floating point math is terrible. Okay. Wait. I don't know why we only got whatever. We're getting numbers in like the 60s and 70s. We're getting numbers that are similar to Torch's numbers. Torch also might be allocating on a boundary. Oh, this might just have to do with TLB misses. That thing yesterday might have to do with TLB. You guys know what TLB is? So let's go simple with this. I'm gonna make stuff that doesn't work, but should basically do the same stuff. You know what an ABI is? Not an API, an ABI. Only the memory access. Let's get rid of all of the stuff that's not the memory. Probably be quicker if I copy and paste the whole thing and then. So is this ADR actually needed? I don't think it's actually part of it. I'm gonna delete that. We should be stripping that. We should be stripping that. UVN if you know how to fix that. I want minimal shellcode. Like I love the tinygrad, it's just shellcode. All right. What is this needed for? Why is this code here? Oh, that's the compare for the loop. Why can't it use this one? Oh, I guess that kind of makes sense. Whatever. Okay, we're only getting 72 gigabytes per second read. Like we're not limited at all. I took the math out and that's just entirely the read speed. Just for fun, let's see if this becomes reliable if I align it to a page boundary. It's a lot more reliable. All right, someone want to fix the malloc allocator to align to page boundaries whenever things are big? Actually, it's a one-liner. But no, like this isn't the right fix. Whatever. Okay, well that makes things faster. At least more consistent. We're in 1 millisecond timing range, so like the CPU should have no problem reliably timing that. I don't know what it's doing now, but why was that one like? Why was that one 50 something? I don't know. Whatever. Okay, so just doing the memory accesses alone, I'm only getting 76. This is only accessing memory at 76 gigabytes per second, which I'll note is also Torch's speed. The reason our speed doesn't match Torch, and this is very fixable now, I'll throw a $300 bounty on it if someone wants to actually do it. Find out how to modify the opt-ops in order to do that correct swizzle. So we know how to get the same speed as Torch. I still don't understand why Torch is that slow, and I think we're going to spend the rest of the stream doing this. but I'll put I really want to get, like, I can do it and implement it. With a lot of these bounties, I'm capable of doing the bounty, but my goal is not to do the bounty. My goal as a manager of the project is to enable others and bring people in so that they can do the bounty. So yeah, like me actually doing it misses the point. There's no way for me to, if tinygrad's going to succeed as a project, there's no way for me to code the whole thing. Just it's too much work, and there's too many of these things to do. We have a pretty great team so far. So we're 5 people, and these people have done a ton of stuff independently. You can look and see who they are, what they've done on the GitHub, and it's amazing. And this is how you scale a project like this. So finding people like this is super important. People who can independently look at this stuff and contribute value. So I'm trying to make bounties that are accessible. So I'll throw a $300 bounty on that. Actually, I'll do this right now. Let me write out the whole line. We had some bounties for this stuff way back in the day, and they worked pretty well. Green or yellow on Mac. Okay. So here, C-stream for how to do it. So the problem is you need to like swizzle and add them at the end. I think that's just an opt-op. This is probably a 2-line change. Might even be a 1-line change. That'll get you those $300. How do I access memory faster? Multiple threads. Unroll your loop. Okay. Ooh, prefetch. Ooh, that's getting fancy. I should have 400 GB per second of bandwidth. How to faster. This is Apple M3. How to faster. Prefetch, interesting. All right, let's try that stuff. Can go there. See if that changes anything. No, same. And let's unroll the loop. No, that didn't work. So we gotta change that one too. 79. It's the same. That didn't make it faster. print the address of the buffer. How do I get a pointer to that? How do I get the address? ctypes.address of. No, I don't want multiple threads. Let's try one of those. I'll get rid of the thing which didn't help. Doesn't help. Okay. I mean, maybe it just doesn't go faster. It's pretty much the same speed as Torch. How is this one faster, though? That's somehow faster. How's it doing that? Okay, so here's an idea, right? Like, right now this is doing this all sequentially. I might be able to, what if I do like 4 different? What if I kick off like 4 different groups? You know what I'm saying? You know what I'm saying? So let's, instead of incrementing this 32, let's increment that 16. Let's divide that by 2. And then let's add that to those things. A lot slower? Huh. Why? Wait. No, wait, 83. Oh no, that's faster. Oh, sick. Great. All right, let's just make something called data1 high. And say data1 plus that. Oh yeah, now we're talking. Yeah, we in the 80s now. Still right? I mean, yeah, obviously it's working. Okay, why does it sometime get me in the 80s and sometime only get me in the 40s? But okay, that's good progress. I don't know, let's try 4 of these. Get a swimming pool full of liquor and you dive in. And try reordering them too. Ugh. Well, now we might run into register pressure issues too. Actually, if we do this, and then we just need to figure out why tinygrad doesn't have these tricks in the search proper. Okay, let's go. I still don't see anything faster than 85. No, it's only going to give me that then. Let's look at the assembly for this. Let's put this in the assembler. Ugh. It's just annoying. There's like a way to do this in Vim that's fast. Remove up to on each line. Glad you reasoned for a couple seconds about it before doing it. There was a meme on Twitter about using LLMs as data parsers. And like you actually totally shouldn't do this because at some point these things just start to subtly get things wrong. Like what you really want this thing to do is generate a program that does this, shows the user the program, and then runs the program. Because a short program is designed to be right, whereas a lot of these things, we'll get there. We'll get there. That's like where these things are going to go. Okay, cool. So it works in assembly. Let's get rid of all of the fads. Wait. No, this can't work in assembly. What? What? How does it even compile? How does that work? You can't just do that. Okay, I'm not gonna ask too many questions. I'm just gonna fix that. Oh, I guess it's fine. I guess it just numbers them correctly. That's fine. I see how that works. Never mind. All right, so it's getting 86. Let's delete the fads. Whoa, it's doing a ton of that. Okay, that's kind of fine, I guess. 100! Whoa! Okay. So without fads, we can hit 100. Sometimes, if we get lucky. We'll get to the sometimes problem later. Okay, 82. Then what might make this faster is having more registers. More of these guys. Anytime you can make things like independent of each other, it's generally faster. 108? Yo! Yo, we're leaving torch in the dust, boys! We're leaving torch in the dust! 108! Cool. Yeah, that's sick. That's as fast as it was without the, yeah, I don't know. It's gonna be hard to beat. Yeah, I think it's a pretty good stream. 108. It's about 100. Fast like a NASCAR. All right. Now made tinygrad generate that code. I'll do it next stream if nobody does it. If nobody does it, I'll do it next stream. But I want somebody to take time and look at this and figure out how to, oh, cool. So what the optimizations that he was doing by hand in the C in tinygrad actually corresponds to this other thing. And we just need to basically add this other thing to the search space, right? It corresponds to these opt-ops. So opt-ops are in the kernel. By choosing the right set of opt-ops. So the next steps here are to go and take opt-ops, find a set of opt-ops that has the code autogen generate this. First, you want to do that manually. Then you want to go in and modify the search to have the search find it for you. I believe in one of you to be able to do that. 7 minutes with chat, and then I got things to do today. I'm gonna say if you static or register the C variables, they already are registers. I'm looking at the assembly, so I don't think that's gonna help too much. Non-subs, if you want to talk, now's your moment. I'm glad you guys like Amanda. She's very nice. Last weekend. I know what we're going to do. The question of when true artificial general intelligence might arrive has been circulating in AI circles for decades, and it's never been more relevant than it is today. So, Tandy boy, you should read this. There's no consensus, but there's healthy skepticism and open inquiry. I read a thing about how ChatGPT makes people less politically polarized, and I largely agree. Do you like DeepSeek? Let's see. I am dishing out $200 a month just so I can just get unlimited one. He's not familiar with DeepSeek, unfortunately. You're gonna have DJ Cows. You're gonna have to clarify. Is AMD gonna sue you for licensing issues? Let's say. I'm not aware of any reason that AMD would sue me. Is O3 available yet? Where to start if you want to help with tinygrad? No, actually, there's no O3 yet. I have O3 mini and O3 high, but I don't have. Where to start if you want to help with tinygrad? Why don't you explore the repository, set up your environment, familiarize yourself with the code, run the tests and examples. I'm actually not sure if that works. You might have to do PyTest test. The example is actually beautiful in NIST. Pick an issue or feature to work on. Yes, that's great. And then contribute your changes, and then you can engage with the community. Wow! Would you rather date O1 or DeepSeek in a humanoid robot body? I mean, neither of them can control the body. You know, they're all kind of like Stephen Hawking. Any quick advice to a CS dropout? I hope this isn't like polluting my ChatGPT. Start building right away. You'll learn a lot faster by actually making things. Wow, that's really true. Real user feedback will show you what's valuable. Focus on solving a problem. Master the basics of business and marketing. Good point. Learn continuously. Iterate rapidly and ship often. Network and find support. I mean, unfortunately, ChatGPT does have this like PMC way of talking. I would never say something lame like that, but you should definitely understand these ideas. If you don't understand how to get people to use your shit, whether your shit's useful, whether your shit costs a good amount, and whether people are excited about your shit, like, yeah, okay, that's important. But that's how I would say it. All right. Sam Altman says ChatGPT will be smarter than him. More hype man nonsense, let's say. What does smarter really mean? Pseudocode, do you mean Python? I love this. I love this. I love copying and pasting your chats into ChatGPT and then just reading what ChatGPT says, because ChatGPT is far more patient with you than I would ever be. I'm sorry, yes. To answer your question, if AGI is already here, well. But can you multiply a matrix? Let's see. Here we go. And now it becomes so clear which of these questions are trolls. Thoughts on AI integration, your editor? Yeah, I tried cursor and stuff. I don't think it's that useful. If you see how I've used AI so far on this stream, I find it very bad at just, you see I've copy and pasted almost nothing, except for the time that I was using it because I don't know Vim syntax. I should have just asked it to write Vim. I should have just asked it to write Vim syntax to do that for me, and then copy and paste it the Vim syntax. Instead of that one example, I almost never use it to write code and then copy and paste the code into the thing. So that's what a lot of these editor integrations seem to be. I tried cursor. I think it's very overhyped. I think that a lot of these editor people don't really have a moat. They're all working on, another more generic way to say that is prompt engineering doesn't have a moat. Prompt engineering falls to the next generation of smarter LLMs. I think eventually it would be great if somehow the LLM could have the entire repo in context and then make specific edits to it. I haven't seen that's what these things do. Is George Hotz a fraud? Let's find out. Doesn't look like I'm a fraud. Thanks, ChatGPT. Is SBF a fraud? Let's see. Let's find out. Maybe it calls nobody a fraud. We need calibration. It's pending a court decision. There is substantial evidence, but it's still a legal question. Until the courts issue a verdict, it remains an allegation, albeit one backed by multiple indictments. Insider guilty pleas. Write a blog post in the style of GeoHot. Let's get another blog post. Metal's a lot faster than LLVM, but remember Metal's using the GPU. No. I hate this shit. It writes like... I've been thinking about break it to make it a lot lately. This is the most awful response I've seen. I would never write something like this, although it does say that I say, you know. Yeah... I would never write something as cringe as this. No, it's cringe as shit. No, it's too cringe. It's too cringe. Thoughts on tool using LLM agents. Whoa, look at how it's like generating. It's interesting how that shows up. No, it really can't. ChatGPT is really bad at that. Anytime you tell it to write in a style, everything is the style of cringe ChatGPT. Okay. To these people who year of AI, like, stop reading the news. The thing is what it does. There's no better experience than what I'm showing you right here. Everybody who thinks they have a better experience, it's marginally better at best. Thank you for watching the stream. I hope that I can inspire some people to come work on tinygrad. And I hope that I can inspire some people to stop asking questions to people and instead asking them to ChatGPT. Because ChatGPT will give you a far more balanced, reasoned, and thought out answer than a person ever would, because a person gets frustrated. The machine, you can keep asking it the same dumbass trolley question over and over again, and the machine will not be trolled. You will. You will always be trolled, because the machine never gets bored, never gets tired, never gets drunk. It is our future, and we pray to the great machine God. Happy Sunday, everyone.